Hi again, everyone. Welcome back to our course in college algebra. In this video, I wanted to review how to graph quadratic functions, in particular when the function is given to us in vertex form. Now, as we discussed early on in this course, the class is all about functions. Different types of functions are used to model different types of behavior. We've seen linear functions already, and they're very easy to write down because their graph is a line. So if I gave you the graph of a linear function, you could write down the formula for that linear function by finding the y-intercept and then figuring out the slope of the line. And you could also go the other way. If I gave you the formula for a linear function, I would expect you to be able to write down the graph very quickly. But not every situation can be modeled with a linear function because linear functions are either always increasing or always decreasing, and they are doing so at the exact same rate throughout the domain. But that doesn't always happen. This example I've used a bunch of times. Chalk goes up and then it comes back down. So to model the height of the chalk, I would need a function that starts out increasing and then starts to decrease. So a different type of function is called for. In fact, that can be modeled, as we'll see later, with a quadratic function. Okay, so the vertex form actually makes it very easy to graph any quadratic function that we're given by shifting around the basic graph. Now, how do you know you're dealing with a quadratic? Well, it involves squaring the variable. Okay, so linear function, you just have variable to the first power, that's it. Absolute value function, which we've dealt with in this class before, they're V-shaped graphs. Absolute value function, you got the variable inside the absolute value operation. When I say quadratic function, we're talking about something that involves the second power of our variable. Now, let me draw a quick graph that we'll refer to over and over again. What I'm drawing right now is part of the graph of the equation or the function y equals x squared. You notice I was plotting some points over here. 1, 1 is on this graph. 1 goes in, you square 1, you get 1, so input of 1 produces an output of 1. 2, 4 is on this graph. You take 2 and use it as the input. 2 squared is 4, so 2 goes in, 4 comes out. So 2, 4 is on the graph. Of course, we remember that the graph of a function is the set of all input-output pairs. Another point that I plotted was 3, 9. Use this as the input to the squaring function, you get 9 out. Okay? We've actually discussed this a couple times in our class, but when you square a real number, you always get a positive result. If you take a positive number and square it, you're doing a positive number times itself. Positive times positive, you get a positive. If you take a negative number and square it, you are doing a negative number times itself. Negative times negative also gives you a positive. So we would have these points on the graph of our function. Okay, now I want you to notice on this portion of the domain, the function is increasing. The function is increasing on 0 to infinity. And not only is it increasing, it's getting steeper as we go. So 1 unit over, 1 unit up. 1 unit over, 3 units up. 1 unit over, 5 units up. So the increases are themselves increasing. That's why this graph bends like this. It's not a linear function, because a linear function, if it's increasing, it's always increasing at the same exact rate all the time. This function, on the portion where it's increasing faster the further out you go. Okay? So, I want you to keep this shape in mind. Whenever you see a function that has this form, this will be the basic shape that you deal with. And you can get the graph of any function given to you in this form by applying the principles that we discussed when we were dealing with absolute value functions. It's a special case of something we call transformations, okay? Transformations let us look at changes in the formula and figure out how that affects the graph. Okay, so this multiplier out front, the lead coefficient, will tell you whether the graph opens up or opens down. We'll look at a couple of examples in just a minute. In here, this will tell you how to move the graph either to the left or to the right, and this will tell you how to move the graph vertically. So this will be your vertical reflection and stretching, horizontal shifting, vertical shifting. You can apply them in that order. Do this first, do any horizontal shifting, and then do your vertical shifting. Okay, let's do a quick example. F of x equals x plus 1 quantity squared minus 3. Okay, let me draw myself a nice grid. Okay, when I'm doing this, I'm working pretty hard to keep my tick marks evenly spaced. Okay, so we know the principles of translations from the work we did with absolute value functions. Okay, I see that this involves the squaring function, so this is my basic graph. The input x has been replaced by x plus 1, so that will shift us 1 unit to the left. I've also got a minus 3 outside the function. That's affecting the output, in other words, the y-coordinates of my points on the graph. We're going to get a shift of 3 units down. Okay, now ordinarily, this point here, this vertex, is at 0, 0 in the basic graph of the squaring function. Think about the moves we just said. We're going to go 1 unit left, 3 units down. So starting at 0, 0, which is where the vertex was in the basic graph, we go 1 unit left, 3 units down. This is our vertex, -1, 3, okay? This is called the vertex form because you can just look at the formula and tell where the vertex is going to be. Now, a couple of more things, okay? I want really accurate graphs. I want to be able to look at my graph and tell, if I put this in, here's the output, okay? So I'm going to move some other anchor points here. Remember when we were looking at this original picture, 1 unit over, 1 unit up, 1 unit over, 3 units up, 1 unit over, 5 units up? Remember those jumps, 1, 3, 5. Okay, that's what we're going to do here. 1 unit over, 1 unit up. This point is on the graph. 1 unit over, 1, 2, 3 units up. There's another point on the graph. 1 unit over, 1, 2, 3, 4, 5 units up. All right? So we go ahead and we connect these with a nice smooth curve. Pretty close to a nice smooth curve. I was wavering there a little bit, a little indecisive, but you get the idea. Let me kind of plot those nice and big so we can still see them. All right, now, as you probably noticed over here, there is a certain symmetry to this graph. The left-hand side is a mirror image of the right-hand side. Now, of course, that's not going to happen across the y-axis in this picture, but it is going to happen across this line. Okay, so see this point is on the line. I can go 1 unit across and get another point on the graph. This point is on the graph. Well, it was 2 units away from the line. I'll have a point kind of symmetric there, and then 3 units over there. Okay, so let me check my work here. So my claim here is that if I put in 1 as my input, I'm going to get 1 as my output. That's what I'm saying here. 1 comma 1 is on the graph. Let me try it. I put in x equals 1. Substitute in x equals 1 right there. That means I replace that with a 1. 1 plus 1 is 2. 2 squared is 4. Minus 3 is 1. 1 goes in, 1 comes out. What's my claim here? That is 2, 1, 2, 3, 4, 5, 6. 2 comma 6 I'm claiming was on the graph. Okay, put in x equals 2. 2 plus 1 is 3. 3 squared is 9. Minus 3 is 6. Okay? So because I was very careful in constructing my graph, I can use that picture to read off input-output pairs, so that's a very useful graph right there. All right, so inside the parentheses, you're dealing with your horizontal shifts, moving you to the left and to the right. Outside the parentheses, you're dealing with vertical shifts. And remember those jumps, 1, 3, 5, from the standard graph. All right, let me do another one for you. Let me throw in a multiplier out front. Negative 2 x minus 3. How about we do plus 5? Okay, negative 2 x minus 3 plus 5. So let me see here. Draw myself a grid. Once again, being careful to space my tick marks nice and even. Okay, so I'm looking at that multiplier. That multiplier is negative. Oops. I think I said squared, but I didn't write squared. Okay, so that multiplier is negative. So that is going to take our basic graph and reflect it across the x-axis. So you're going to have a reflection there across the x-axis. This is going to stretch by a factor of 2. I'll show you how to incorporate that in a second. You're going to go 3 units right from the origin where the vertex is on the basic graph. 3 units right, 5 units up. Okay, so 1, 2, 3 units right. 1, 2, 3, 4, 5 units up. So this is my vertex. 3 comma 5. So once again, it's called the vertex form because you can just look at that expression and get the coordinates of the vertex by taking the opposite of this and then that by itself. So that's my vertex. Now the ordinary graph would start at the vertex and go over 1, up 1. Okay, well, because of the vertical reflection, we're going to go over 1 and we're going to go down. But we're not going to go down 1, we're going to go down 2. Okay, so over 1, down 2. Okay, that's my first jump. Remember, I'm thinking 1, 3, 5. Those are my ordinary jumps. Here I got to reverse them. I don't go up 1, I go down 2. Next ordinary jump was over 1, up 3. I'm going to go down 6. Hopefully I left myself enough space. 1, 2. Okay, down 1, 2. Okay, right there. So over 1, down 1, 2, 3, 4, 5, 6. Okay, there's just enough room for my next point. All right. Okay, so I got this side. Once again, connect these with a nice, smooth curve. Your graph is going to bend, and it's going to have a pretty sharp bend here to make this line up work. So what's my claim? My claim is that 1, 2, 3, 4, and I was starting at 5, and I went down 2. So my claim is 4, 3 is on the graph. Let's check it. Put in x equals 4. 4 minus 3 is 1 squared. 1 squared is 1 times negative 2 is negative 2 plus 5 gives me 3. All right, so over 1 down 2 was correct. Now I'm going to use the symmetry to get additional points for free. Okay, this line right here, x equals 3, that is called the axis of symmetry. So every quadratic function will have an axis of symmetry. It's a vertical line going through the vertex. I use the axis of symmetry to get additional points for free. Notice I was really careful counting out on the left-hand side, or sorry, the right-hand side of this. To get the other points, I just said, okay, I got this on there, so that's going to be on there. I got this on there, that's going to be on there. This is 2 units away to the right, 2 units away to the left, same height. Okay? So, fairly easy to get the graph of a quadratic function that's in vertex form if you've done the practice that we have assigned for absolute value functions. It's the same idea. Right? Inside there tells you what to do horizontally, horizontal translation. This tells you vertical translation. Multiplier out front tells you about any vertical reflections. If the multiplier out front is negative, the graph will open down rather than opening up. And it'll also tell you about vertical stretching. Okay, so all the information is right there for us, provided that we know how to look for it.